Example number 4 from section 5, chapter 1 asks us to do the following. It says differentiate x raised to the 3 halves by writing, oops, one too many t's in there, by writing x to the 3 halves as equal to x to the 2 halves times x to the 1 half, which they're saying is equal to x times the square root of x. Now let's talk about that for a second here before we go, and they want us to use the product rule, and using the product rule. First, we can't just go directly to our power rule because we haven't discussed the idea of having a fractional or a rational exponent up here. We've only talked about using integer values, and specifically non-negative integer values. Or specifically just positive integer values, because we haven't even talked, well, we discussed 0 a little bit. So we've got this situation here where we're rewriting it. Now, this is the jump that I think is interesting to make. This to this guy right here is x squared, the square root, which, by the way, is x to raised to the 1 half, okay, which is x to the 2 halves. Okay, is this equal to x? Now you might say, yeah, of course. When you take the square root, that gets rid of this guy right here. That's not true. Watch. What if we let x be equal to -1? Now, is the square root of x squared equal to x? Let's check it out. So this should be equal to, if x is -1, this should be equal to -1. But watch what happens. When I plug in -1 squared, I get -1 squared, which is +1, and the square root of 1 is 1, and they are not equal to one another. So what we usually say is that the square root of x squared is equal to the absolute value of x. Now that corrects our situation. 1 is equal to 1. Now you might say, well, why didn't they use absolute value here? Well, they didn't have to, and let's go ahead and see why. I don't have to put an absolute value here because the square root of x right here already assumes that x is greater than or equal to 0 by the domain here. So I didn't have to put it around here because we know that x can't be negative. So when we're working over here in this guy, it's already assumed that x is greater than or equal to 0, which is why we don't put absolute value signs here. Now that has nothing to do with the problem, but it does in some sense, because it's not just manipulating symbols here. We actually have to think about what we're doing. Okay, so we can rewrite this as this without having a problem. So let's go ahead and use the product rule here. So we've got x times the square root of x, and we would like to differentiate that. Take the derivative. So our rule is to differentiate one of the guys. We'll do the first, multiply that by the second, and then add to that the derivative of the other guy multiplied by the first. Well, the derivative of x is just 1. The derivative of the square root of x, we've already done that before, and we did it using the limits. Okay, so we check this guy out using the limits. That is going to be equal to 1 over 2 square roots of x times x. So this will be the square root of x plus 1 half. Now x is going to be equal to the square root of x times the square root of x. So this will just give me a square root of x in the top, in the numerator. And so if I combine these, I have 1 plus a half, which gives me 3 halves square root of x, which is the same as 3 halves x to the 1 halves, which shows us, okay, that's the answer, that shows us that if we have x to the 3 halves, our power rule works. We can bring 3 halves down to the front, and we can subtract 1 off the top here, so it'll be 3 halves x to the 3 halves minus 2 halves, which is 3 halves x to the 1 half, or 3 square root of x over 2, which is exactly what that guy is right there. So our power rule will work, okay, when these guys up here are rational numbers. However, we haven't proven that, we've just shown it for one specific case.